Hey y'all, welcome back. We are beginning our second stint of the semester in an online format. Giving it a shot now. This is my first recording, so bear with me. These will likely improve with time. So, where were we? Um, the last couple of weeks, we got into um, the discussion of the physical symbol system hypothesis, right? This has been the focus for a little while, just talking about the idea of the mind as this symbol computing process somehow or another, right? And it's a useful tool. I think we've shown we've seen, even as far back as Sherdlu, we would call one of these systems. Expert systems also. We saw Whisper able to do some that use the same paradigm to solve some inherently non-symbolic problems, and then we even had Shaky able to navigate rooms, right? But there's a lot of ways we can take on the concept of information processing, right? That being the core of what the mind is doing in most camps, I believe. If nothing else, we are transmitting information through our neurons from our sensory organs and out back into the world with motor actions, right? So we're looking at a bit of a different take on how a system might process information, right? In the past, we were treating it as like a sort of symbolic computer, right? Take information one symbol at a time and do something to it. That's the way that most modern computers do actually work. Although parallel processing has gotten a little bit more interesting. So the question is, how do we make those symbols kind of bind to actual meaning, right? You have abstract symbols, the idea of cat, but we also have this understanding of cat, right? We talked a little bit about content versus vehicle, that kind of stuff. We won't continue to focus on that, but the concept is meaningful, and the question is, do we need a sort of symbolic language to handle information processing? In fact, there's nothing inherently symbolic about the way, say, an electrical wire transmits its information, but it still is almost certainly information. That's how telephones work, and that's how the entire internet works, right? That's how you downloaded this app. Pardon my pinging. Didn't put my phone on silent. So, the question is, neurons can handle this sort of less abstracted version of transmitting information. How far can we get with that? So this is where we get into neural modeling. So, if we can describe how neurons work and just focus on that, that allows us to maybe stop asking the questions at the higher level, right? Remember what we've talked about, top-down versus bottom-up explanations. Physical symbol systems are pretty much top-down explanations. They say, okay, there must be a way that I'm able to move language around in my mind, therefore there's, language is symbolic, etc. Let's explain the rest of it by looking down. But from the neural modeling approach, it's actually much more bottom-up. The question is, hey, I can pretty well prove how a single neuron works. What can I achieve by just using lots of single neurons? So this brings us to neural modeling. So we've seen, remember our historical tour, we watched the beginning of being able to take neuroimaging and get a better understanding of the brain, right? So there's been a lot of tools that, this is the kind of technology that really enables us to pin down something that the behaviorists never thought was possible. What exactly is the nature of a neuron and how does it work? So we've had a lot of different tools. We can measure very, very small spiking patterns. We can also measure whole brain, how information moves around in the brain. And we have this increasingly clear understanding of the machinery of the neurons and the overall flow of how, what different brain regions are more or less used for. So this is, but you might see a bit of a disconnect here. So neuroimaging is really coarse. It's really like high level. Again, it's always levels, but it's a broad picture of how information in the brain works. Whereas single unit recordings are really, really fine grained, and they don't situate how a neuron works, among the rest of the neurons. It's sort of too focused. So, we need to have some understanding. You can see maybe here a call for this, an understanding of how that overall flow makes sense in light of the machinery that we're really getting a good picture of. So to kind of like take a sidestep into a related topic, if I understand how all of the pipes and machinery in my car work, and I also have this overall sketch of the car as sort of the way its machinery should move and flow. We know that a car should drive. We know that it must combust fuel to be able to achieve this. That's a sort of computational level explanation, whereas the pipes and the different hoses and, all of the different machinery moving around in your car are the sort of very low level, the implementation level. What we need is an algorithmic level explanation to really understand how the car works, right? We need to understand what flows where, when, are there timings involved, what pressures are on the system, we can't just blast all of the fuel at once, our car would explode, right? So I hope this illustrates that, the car, the overall schematic of the car is one thing, and the machinery of the car is another, and there is this sort of middle ground of asking, how do these two ends meet? So it's a very, algorithmic approach. So this is where computational neuroscience is born. It's pretty cool stuff. It's all over the place these days. You've seen it, whether you know it or not. You've definitely seen it. So remember, computational modeling, right? We talked about this a little bit. Computational models are the kind that try to simulate specific behavior patterns one step at a time, right? That this is for systems that are way too complex to model them perfectly, sort of mathematically with very clean functions. This is the computational approach. So computational neuroscience is saying, hey, if I can pin down how a neuron works and I can set them up to connect to other neurons, let's just see what kind of information processing we can actually build out of this. The answer is quite a lot, but not all, right? We have not yet solved the human brain and created a false brain. It's not even really the goal. It's more about understanding things. We'll get into more interesting examples of how this is used in real life as this unit wears on. So let's talk a little bit about neurons. Remember them as the basic. They're the focus of computational neuroscience is neurons, right? It's very bottom up. What are some things that we know about neurons? We haven't touched on this in detail yet, but there's just a few pieces of how a neural cell works. It has sort of, this is the front to back flow. There are dendrites that collect, signals from information from other neurons around it. A cell body, which will create that sort of synthesizes that signal into, hey, am I going to fire or not? Which then the axon is what takes that signal forward to somewhere else to trigger other neurons. And at the end, bulbs, that's how a neurotransmitter is shot to the next neuron and, over the synapse, and we create it. Let's see an image of that now. So, dendrites, information comes in, the cell body integrates that information, axon sends it out, and then we actually send a signal to the next neuron. Now, to illustrate that, we have information comes in on the left here into the dendrites. Information is this lightning bolts. And then when enough information comes in, the cell body gets excited and it sends a signal down the axon, which then propagates the signal across the synapse into some other neuron's dendrites. It's all very biological. If you take the Brains, Minds, Consciousness course, we'll touch on that more. Or if you take any neuropsych course, you'll learn more about this. It's kind of fascinating. But the idea is that this is how we biologically achieve sending sending information over the quote over the wire, right? So, let's see. Other bits to know about a neuron. Their patterns. It's not just I'm firing or I'm not. There's also how quickly am I firing? Am I firing very slow, or really fast? You know, this more sort of there's so that means that there's a lot of breadth of information that a single neuron can actually fire. It's not just an on or off signal. It's sort of a firing pattern. Also, a tidbit about this that is really important, especially if you understand a little bit about algorithms and as implemented on computer chips. It's really important to have the ability to both increase the firing of a nearby neuron, but also decrease the firing of a nearby neuron. There's sort of a way to say, if I am active, I'm going to try to shut this one down. Whereas an excitatory connection would say, when I am active, I'm going to try to excite this other neuron into acting. Whereas inhibitory is, I'm excited, I'm going to inhibit this other neuron from firing. This is really useful for processing information. So let's see. It's fairly straightforward, I hope. I hope that it's clear how this works. I catch a signal, and then once I get enough signal, I pass it forward. I release it forward, right? And then I repeat. So the question is, this is really a complex biological process, right? Is there a way that we can reduce it to a form that is pretty predictive of how these actually function? So can we model a single neuron using kind of a reduced mathematical form and then achieve our computational goals of, I could process hundreds of neurons, millions of neurons simultaneously, and just see how the information develops over time. So that's where we get into the artificial neuron. So this is a way to capture the firing patterns, the informational elements of a neuron mathematically at this algorithmic level, right? That's what we needed in the spread between our broad neural function understanding and our individual neuron understanding. So this is the basic way that this works. The inputs of an artificial neuron are numbers, just a signal of, it can be a firing pattern, so it could maybe be sort of a real number, or it could be just an on or off signal. So some information is coming in, and it will then get weighted and combined in the core of the cell, the quote cell. A better way to refer to these is as a node. So is this clear? So the idea of the question ultimately is, am I this neuron going to send a signal forward, right? Just like in the biological version. The way that works, and you can see that S on the right side of this little diagram. So if the signal is the goal, the question is, when should I fire that? The idea being that I might have a bunch of inhibitory connections trying to slow me down, and I might have a bunch of excitatory connections trying to speed me up. And I need to combine all of that somehow to figure out, hey, am I going to fire or not? So there are a lot of different ways to characterize the behavior of a neuron. Different neurons kind of behave a little differently, and even just in January, there was a new publication saying, hey, there's a neuron that can capture a different function. Like, oh, amazing. Oh. So let's talk about activation functions. Any given neuron will behave a little differently than other neurons. And we're going to talk in terms of the sort of mathematical approach to that. So they could just be binary, right? I'm either firing or I'm not. That's a very simple way to approach this. And in fact, we're going to focus on that in as we discuss some of these simple neural networks. But there's other ways that neurons respond, right? For example, a real easy one is just take your thumb and press it into your forearm. Now, if you press lightly, your neurons are firing only a little at a time, right? If you press really hard, they fire a lot more, right? Now, I don't press yourself too hard, but it's don't bruise yourself over this. But the idea is that those are the same neurons, right? Those are the same neurons in that same little patch of your arm, and they are firing more and more often because you're giving it a stronger signal. That means that it's not just binary, it's not just on or off. There is a sort of a pattern to it. So we can talk about a few different activation functions. First, the simple version is binary threshold. That's simple on or off. When my input crosses a certain threshold, I start firing, and I just stay at the same rate the whole time. If that threshold if all of the input coming into my cell ever goes back below that threshold, I stop firing. That's good for binary neurons, but there's other ways to sort of capture this. There's the linear function where this kind of like this may be roughly how your arm handles this. The more you press, the more the firing rate goes up. It's just a straight linear relationship. You see in the upper left there, the binary threshold being in the bottom right. There's also sort of a combined approach, threshold linear, which is the neuron won't respond at all until a certain point, after which it is, again, linear. So maybe a neuron that, for instance, maybe the way that you detect heat, right? Like a hot surface. You don't have a whole lot going on most surfaces. It has to get to a certain point before you start to respond with, oh God, that's hot. Or rather, ooh, this is warm. Oh God, this is really hot, etc. And there's a little bit more nuance to it even than that. There may be sigmoid functions where it takes a while for there to be any response at all, but then there's a big jump, and then you get less and less returns. Point being, there's variety to how neurons function, and that's an interesting thing. This is a continuous area of research in our world, but this determines how your individual neuron, how you should model it, right? If I have a linear function, I'm going to do different things with my algorithmic math to say, I should be firing at a different rate, etc. So this starts to paint the picture of how we might be able to model individual neurons. In fact, I'm going to jump back real quick to this, right? So our artificial neuron, right? Again, it takes inputs, it combines those inputs to, some of them were negative, some of them were positive, and then it decides, hey, am I going to fire off or not? And you might have different functions for the output end. That brings us now to, okay, that's a pretty good picture of how a neuron works. Let's talk about how we can combine them. So this is where we get into neural networks. We talked a little bit about this when I described, sort of how you might parse out the image of a cat a few lectures back. But this is just a collection of artificial neurons that are all wired up to one another. And the goal being they want to process information somehow, right? So the outputs from one neuron, the outputs of one wire, in quotes, will influence the next wire, until on the output end we have some sort of information has been processed. For instance, the cat, I detect all the edges of the cat, I detect the different features of the face of the cat, on and on, keep abstracting up until, aha! I've arrived at this pattern in my brain that says, I want to pet that. So you can see sort of how this flows, I think. And so this idea is the whole framework for how computational neuroscience approaches things. They try to make neural networks that achieve specific information processing goals. So where does that leave us? We are at the point where we can model algorithmically a neuron, right? And now we can start to ask questions about, okay, cool, if this basic neuron is somewhat knowable to us in an algorithmic way, we understand its inputs and its outputs and how to modulate them. How do I get from that super basic form to be able to do all the cool things that we do every day, right? High level reasoning, philosophy, art, science, sweet cake flips. So that's where we have to start from somewhere, right? We need to bridge the gap from the very simple information processing capabilities up to the cool stuff, right? So, a good place to begin with this is in the binary world. So, let's talk a little bit about very simple operations, binary operations. Remember, we talked before about how the most basic form of information is a bit, right? A yes or a no, an on or an off. You need one bit to capture the result of a coin flip, right? It has two possible states, and that's it. You may not know, but bits and binary and what's called Boolean logic has a whole suite of functions, and you use these every day. They're logical functions, and we use these. I mean, these are used all over the place in computers, and they're the most basic thing that you can do in logic gates in computers, and they allow us to do. You can build all kinds of other stuff out of simple Boolean functions. So let's look at some of these. There's a lot of these, and then there's actually even more than what we're seeing here. This is just a handful. The simple ones are at the top. The things that we kind of use in everyday life, more or less. Not is just a simple inversion. If I have a 0, it becomes a 1. If I have, or false becomes true, true becomes false. So, if I'll have a slice of pizza provided it does not have mushrooms on it, right? That's the opposite of I'll have a slice of pizza provided it has mushrooms on it. That not operator changes your understanding of that sentence, right? Now, and is the requirement for both, right? I need both mushrooms and pepperoni on the slice for me to eat it. Or maybe I'm a little more relaxed and I'll have an or scenario where, hey, it could have mushrooms, it could have pepperoni, it could have either one, it's fine, right? So you see a little bit here how the function works, though. If both food items are present on the pizza, then both and or evaluate to true, but or is the more lenient version that says, hey, if either one of them is present, I'll take it. Whereas and is more restrictive. Only if both items are present. See the one, and the one there. Show only in that case am I outputting a positive signal. So you think about these in terms of the combining the input signals to create an output signal with a particular operation, right? This is the simplest form of trying to capture some kind of computation in a very simple algorithmic way. So these are the kinds of things we're going to try to model using artificial neurons, simulated neurons. So exclusive OR is another one. This is the more common way that we actually use OR in English. You could have this or this. You don't typically mean you could have either one or both. You typically mean it's an exclusive OR. I only want one or the other. And we also have these a little bit weirder versions, things like nor. That's only true if neither A nor B is present, right? I want neither mushrooms nor pepperoni on my pizza, right? We don't typically say it in such terms, but you're getting the picture. So these are all simple logical operations that we do them every day at the human level using language and all that stuff. But it's also a more fundamental question of how can I move information around and transform it into something useful. So how do we capture these in neurons? And the answer was the initial introduction of the perceptron. So the perceptron is an artificial neuron, but it's a little bit simpler, and it's designed exclusively to deal with Boolean functions. Or designed to deal with Boolean stuff. It can handle a little bit more than that, but primarily it's about Boolean logic. So artificial neuron, it has the same basic concept, right? It can take a set of inputs through its, quote unquote dendrites, and it will then propagate a signal once it reaches a threshold for activity, and then it will output a new signal, right? So it takes inputs, those inputs will have a particular weighting to them, and then it will potentially output on or off. There's a firing threshold that determines whether or not you actually fire, right? So the function is determined more or less exclusively by how you set up your weights and how you set up the threshold for the activation. This is kind of how neurons work. It's not perfect, but it's pretty accurate. So what we're showing here is this is a sort of an algorithmic abstraction of individual neurons that then we can combine into something bigger. So let's look at how a few of these single neurons modeling will actually capture some of these basic Boolean functions. Let's start with the simplest one, not. So what's the function of not? Remember, the input is supposed to be reversed, right? So if I input a 0, I want to output 1. If I input 1, I want to output 0. The way you can capture this is I have the input coming in, right? And then the weight is multiplied by the input is multiplied by the weight of -1, right? And we set the threshold just below 0 so that if this value is 0, I'll output 1, right? This is just math. I'm just saying when the threshold is set just below 0, if my input is 0, it doesn't move at all, so it just gets output. We've inverted that signal. Same as it's the same case for the opposite. So if a 1 comes in, it gets multiplied by -1, and now it's way below the threshold, so no firing happens, no output happens. We see we've captured the not function. Neat. This is a single simulated neuron that is able to take a signal and invert it. That's big because where we're headed with this is being able to invert information is a huge part of being able to detect things like differences, say in a larger scale image, right? There's more. The more of these things you get going on, the more fancy you can get with the complexity of the processing that you can do. Let's look at and. And is more complex, so we'll hang loose on it for a minute. Okay, how do you capture and? You need to be able to say, okay, I need both things for me to fire, otherwise I don't fire. Okay, so to set that up, you would have two inputs. I need both things. One input is mushroom. The top one's mushroom. Input 2 is pepperoni, right? I need both. If only one of them is present, I don't want to fire. How do we get there? Well, we can just make the weights both just +1. Don't have to screw with those much. Just leave them as, hey, just send the input forward. But we can set the threshold high enough that it requires full activation from both of these other nodes to make me fire off and say, okay, good. Both of my preferred toppings are present. I will eat this pizza. Okay. Again, the key thing here is that we're showing all you need to change are the thresholds and the weightings to capture a whole different function. And we can see here that let's walk through it a little bit. If I get 2 zeros, those get multiplied by 0, 0, 0. You know, my value is 0 inside of in the center node. I'm not above the threshold to fire. I don't fire. Same with either of just getting one or the other one, right? My total signal inside of the cell, quote cell, is 1. If I only have one or the other, I've got 0 times 1 and 1 times 1 getting added together. So I end up with not enough to fire. I need to cross that 1.9 threshold, which is, again, set just below 2, right? We could say it's 2, but we're more accurate this way. So by doing this, we've captured, again, we've taken 2 inputs and we've created an AND function. That's super useful. This is the kind of stuff that allows you to combine information, allows you to transform information, right? We're developing the basic logical circuits that you might see in a real computer in terms of neurons, simulated neurons, but still things that are neurologically plausible. Let's look at OR. OR is the same as AND because it's still sort of a summation thing, but if we set the threshold a little lower, well, hey, we can make it. We can make it with only one input. So let's set the input at 0.9. The only time I'm not going to take this slice of pizza is if it has neither of my favorite toppings on it. So as long as it has at least one, then I'll fire. And that's exactly what this shows. We have the input 1, let's say that's a 0, but input 2 is a 1. That means we get 1 full strength signal and 1 0 signal, and we add those together, we cross the threshold, right? We cross that threshold at 1, we fire. So this is showing how you just, again, a subtle change, I mean, not subtle, but a single change to the threshold value on the perceptron lets you capture yet another Boolean function. Cool. So, great. Yay. Where is this heading? So there's only so much you can capture, honestly, because of this concept called linear separability. So a single perceptron, we're kind of seeing the edges of it, of what it's capable of, right? A single perceptron is capable of capturing a lot of simple Boolean functions. The only ones it's able to capture, though, are considered linearly separable. Basically, the idea is, am I actually able to capture this function with just a single threshold? What we've sort of seen here is, yes, I can draw a line in the function to say, oh, I can easily separate the outputs that I'm going to have to use here, right? So what this means is that if you have a more complex function that isn't so linearly separable, it's not easy to draw a line in the sand where in the space of possible outputs, you're going to need more than one perceptron. You're going to need multiple perceptrons. You're going to need a small population of perceptrons. And so we're finally getting into the idea of combining these really simple rules and logical operations into more complex things. So let's revisit XOR, right? XOR, we can see, is not linearly separable. I can't just draw a line in the sand and, therefore a sort of a threshold to say, hey, at this point is when I should fire. Because there's 2 points at which I need to make a decision about firing rate, right? With XOR, I only want to fire if only one or the other is presently there. So we can talk about the XOR operation in perceptrons. in the terms of a small network. So this is a little bit fuzzy. Just bear with it. We'll walk through it carefully. So XOR. Remember, we want if the inputs match more or less, we don't want to output anything. We only want to output if the inputs are different, right? Exclusively one or the other is on. So how do we capture that? Oh my goodness. Where do we start? Well, we only have two inputs no matter what, right? But we can wire them both up to two different perceptrons, because why not? I can say, hey, my inputs 1 and 2 go over to this perceptron, the AND at the top, and they both go over to the OR. So this gives us, sort of skip the first step, the left half of this thing, and just think about it as I have the result of an AND operation on my two inputs and the result of an OR operation on my two inputs. Now, how do I make sense of that? So let's look at the table at the bottom, and we can see, the AND of the AND column shows the AND output of those two inputs, and then the ORed column looks just like the OR, right? We have the more lenient OR in that second column. So now is when we get into the part where we use these two kinds of information, these processed versions of our input, right? We have this middle step that's changed the information but made it more usable in a different way. So let's try it out. Look at the weights. So the AND is going to get multiplied by -1, while the OR is going to be left as whatever, multiplied by normal 1, right? So the AND will be inverted, but the OR will remain the same. What does that do for us? We've set the threshold at 0.1, so just above 0, let's look at how this works. So with 0, 0, my AND and my OR are both 0. And that means I should be outputting a 0, and that's fine because that works. I have my threshold is just above 0, so I don't cross it. I get the output is 0. Now let's jump to the 1 and 1 scenario. Well, the -1 multiplier on the AND is going to negate the +1 multiplier on the OR because they're both there. Because they are both there, they negate each other, and we don't end up crossing the threshold to be able to fire. In the other two cases, the case where only one of these is operating, we have the negativity of the AND doesn't come to factor because it's a 0, but the positive values from the OR do come into play, and they output a 1, right? But they give the signal forward. This is just follow along, stop, download the slides and stop on this slide for a minute. Try to trace how this works. Follow it with your vision and your hands and all that, because it's hard to illustrate this at the moment. But what you're seeing here is we've taken the raw information and used these middle steps to add new layers of processing so that we can get this more complex XOR function out of the very simple ones. We've created a more complex function from simpler functions. That is powerful. And we've done it at this very, very low level of explanation. So, how do we actually do things with perceptrons? I mean, just setting up a perceptron with these special weights and stuff, that's fine, but that's too much, right? What you really want is to be able to set these things going on their own. And so that's where we get into the idea of training. This is the idea of machine learning. If you give perceptrons lots of examples, you can train them to, you can give them a rule that says, oh, if I made the wrong prediction, then I can update my weights or threshold to change it, right? So I will slowly, step by step, alter my own properties so that I can finally fit the function that you're trying to teach me. We'll talk more about this in future lectures, but this is a big idea, and it comes with their perceptrons in particular have this theorem that with enough training they will find the answer, but that's only true of simple individual perceptrons. So what does all this mean? We've been flopping around here in the Boolean world for a long time today, and I think the key takeaway is that, and you may or may not know this, but you can create all the rest of math from Boolean operations. If you can represent numbers in binary like a computer does, you can do Boolean operations on those numbers to create what we know of as like algebra math, creating actual calculations of real life numbers, So you could make a modern computer out of perceptrons. You wouldn't want to. It would be terrible, but it would work. So the question, though, that this is where the sort of the computational neuroscientist approach comes in and says, well, we don't really need to make a whole computer. They don't need to be, constrained to this computing idea, this idea of computing one little piece of information at a time. It's more about processing things at large in massively parallel units. So lots and lots of small processors doing a ton of information processing all at once together. So this is the concept of neural networks and more specifically connectionist networks. And here are a few things that are some properties of these kinds of networks, as we start to build up into bigger versions of them. They have a few cool features. So the first is that all of the neurons they're working in parallel. It's also great that the rules are very simple. It's that if a neuron can capture a function, then that's what we can do. We are modeling just the individual neurons and how they function in a sort of simple way, and then from there how that combines upward, right? Some other cool features that we'll look at later are they have graceful degradation, so they can handle incomplete or damaged information that's coming their way, right? You can give a network like this a partial pattern and it will solve it. It'll take most of a cat and say, I'm pretty sure that's a cat. That's really powerful, and it's certainly something that seems familiar to us as humans, right? Partial pattern matching is huge. That's part of our everyday, right? They're also capable of learning, which is cool. I mean, like I just mentioned the perceptron update rule, how it can change itself. We'll take another look at that in the future. That's amazing for the system to have a baked-in way to automatically learn things based on what it observes from the world. That's pretty powerful in terms of trying to capture more about how we work, especially given the fact that this is all neurons up, right? So it's modeling information processing in this non-symbolic way. There's no ghost in this machine. It's just processing. So it's good stuff. So the big approach here, what we've covered today, is computational neuroscience is the approach to take this basic unit, the neuron, and try to reconstruct whatever information processing capabilities we possibly can from just neurons. And then, ultimately the goal is to say, hey, how complex can we make this thing while staying bound to biological constraints? So, all right, thank you so much, especially if you listen all the way to the end here. This is my first shot at this, and I'm hoping to adjust and make it better. I'll be posting these pretty pretty ad hoc for the moment, but soon I'll get into a stronger rhythm with them. So this is it. Thank you. Take care and stay safe.